Ladies and gentlemen, welcome to a fifth lecture, a video lecture, companion to the book The Fivefold Sun. This is October 6th of the year 2018, and about 1 year exactly after this book was filed at the Bibliothèque Nationale de France in Paris in late 2017. Today, in this video number 5, we deal with sections 4, 5, 6 and section 9 of part 1 in the Fivefold Sun, which focus on differential rotation in the solar ball. We will discuss the notion of solar differential rotation all the way from equator to pole, which is in fact rather new, and we will try to arrive at a full matrix of from the rigid rotation of the solar ball, which happens at intermediate latitudes at the surface, to the polar rotation and the equatorial rotation of the Sun. This encompasses 256 pages of part 1 in the book, in the paper version. We start with a short introduction with a 3D spherical ball to explain the issue at hand, and then we'll try to find from meta-analysis of solar physics literature what is the time averaged angular velocity at the slowest point in the solar ball and at the fastest point in the solar ball. It so happens that the slowest point is has to be near the pole, and the fastest point has to be near the equator. Finally, we will arrive hopefully at the sought matrix. I show you for now a simple model of a hemispheric part of a ball comparable to the solar spheroid. You see there is a mark over here which marks the latitude of about 5 degrees poleward from the equator of this hemisphere. And one part of the issue today is to find what is the Sun's equatorial velocity in this region. One of the problems, one of the uncertainties is that there are very few tracers equatorward of this 5-degree latitude. There are only occasional sunspots, for instance, that appear there. But the problem to measure a full differential rotation, the Sun rotating fastest near the equator, as we see from observations, and slowest near the poles, as we see also from observations, the problem which is really difficult is with the pole. Because how do you measure a angular velocity when in fact the diameter or radius of the zone in which the tracers will be pinpointed is so small as a pole? Obviously, when we are in just one point, we cannot measure any angular velocity, so we have to settle with some minimal diameter of the polar region in which we will try to measure a rotation. That is a purely mathematical issue. There is also a physical issue that in fact till present we can only measure rotation on the solar, near the solar poles from the Earth. So we cannot in many seasons, depending on the orientation of the Sun, and the position of the Earth, we cannot see much of the polar caps. So this explains why the issue of measuring rotation of the Sun in the polar regions has been a tricky issue. So we start nevertheless now with this issue, the polar rotation. Secondly, we'll see the equatorial rotation. Because of the problem with the line of sight from the Earth, the determinations that are most helpful for arriving at an estimate of the polar rotation in the Sun is a helioseismological one. That is to say, it is based on measures that include the subsurface regions of the polar regions, and in fact include the subsurface regions of the entire Sun. Seismological techniques allow to determine what the velocities in various directions are inside the Sun, at least to some depth inside this ball. We shall see that based on solar rotation profile plots, which were the earliest published helioseismological results, providing a synthesis of the angular velocities across the solar ball inside the Sun. The slowest polar interior angular velocity is less than 300 nanohertz. If we now turn to another tool of display of helioseismological results as to angular velocity in the Sun, these are in the so-called isocontour plots. These are contours of equal velocity inside the solar ball. We have color codes which tell us what is the band of angular velocity that is detected at a certain isocontour plot, or between two certain isocontour plots. And we can conclude from a meta-analysis of published results as of 2010, when this investigation in the frame of the Fivefold Sun project ended, it is about 280 nanohertz, the slowest polar interior angular velocity in the Sun. If we then turn to isotax in isocontour plots, when we now look more precisely at in a graphical display of a helioseismological measurement result, the line itself of equal velocity instead of a band between contours of equal velocity, we arrive at a slightly different result, which is about 285 to 290 nanohertz, again for the slowest polar interior angular velocity in the Sun. These are for polar cap bounded by the latitude of about 85 degrees. We will, in conclusion, without showing the painstaking details of this meta-analysis and the technical assumptions that are discussed underlying these results, we will conclude that the slowest polar anterior angular velocity in the Sun was, as of 2010, about 280 to 295 nanohertz. If we now include the non-helioseismological results, of which there are also a few, this being a technique that is depending on less costly instrumentation and more traditional instrumentation, we have earlier results which don't go up to 85-degree latitude poleward. But with some extrapolation of differential rotation equation are also discussed in the literature. We see these non-helioseismological determinations, that is at the solar surface itself. They are from 275 to 295 nanohertz. The helioseismological results we just cited, and as an overall conclusion, we would settle for a characteristic angular velocity at the slowest polar location, at the polar location where rotation is the slowest, of about 290 nanohertz. This would be slightly below the polar surface of the Sun, but not much below. You see 0.99 radius fraction, plus or minus 0.01 radius fraction. There was no update of this estimate performed in 2010 in the Fivefold Sun as a book, but no contrary evidence surfaced until present, as of 2018, as far as I know. For instance, in 2016, we see in a thesis a well-drawn rotation profile plot based on the data in Larsen and Xu in 2015, in which we have the same similar helioseismological results, apparently updated by Xu, who is one of the founders of the subject matter, and his colleagues as of 2015. We now turn to the issue of equatorial rotation. What is the fastest time-averaged solar angular velocity, which is to be found in the equatorial regions? There are uncertainties which are specific to the equatorial rotation. There are again a few spots in this region. There is dependence on amplitude of the cycle, phase of the cycle, dependence on depth as well. The result of non-helioseismological determinations is in the range of 466 to 472 nanohertz, and from helioseismological determinations we have results that are around a value of 469 nanohertz with a very narrow range. So it is easier for us now in the case of equatorial rotation to conclude that the fastest rotation in the solar ball, which is in the equatorial region, is of about 469 nanohertz. In this table, you see results from recent determinations as of 2010, in which you see that the range of helioseismological findings was from 468 to 471 nanohertz, at depth from 0.915 radius fraction to 0.94 radius fraction. Based on these numbers, 469 nanohertz for the equatorial fastest rotation, and as previously found in the polar regions about 290 nanohertz, we can now calculate a ratio which is the differential rotation ratio all the way from equator to pole in the extreme angular velocity regions, the fastest one and the slowest one, and this amounts to 1.617 or so. So we can also do a sensitivity analysis of this result with the various stated values for the fastest angular velocity in the equatorial region as stated in the literature, and the same for the polar regions, the slowest angular velocity. And we find that all but two of these cases amount to a ratio of 1.618 plus or minus at most 2%. Only two of these values are out of this very narrow bound. If we look now at the estimates of this ratio in solar physics literature, first of all, there is a scarcity of such statements. This has been of little interest to solar physicists so far. The differential rotation from equator to pole was regarded as something that is very difficult to measure and maybe a futile pursuit. So of the few published values, we can see that those that were used in assumptions for simulations of the solar dynamo and other solar physics dynamo, they have a ratio which I found from a meta-analysis from a few mentioned results in the literature of about 1.25. This is from stated equatorial velocities and polar velocities without an explicit ratio. And when in the rare cases an explicit ratio of these two values is stated, we have an average of 1.35. So maybe it is appropriate to say that these estimates are too low and are somehow obsolete. Maybe this is not an exaggeration. Now, where is the depth of the solar rotation where this ratio of about 1.617 is observed between the extreme angular velocities? It is near the surface, at or very near the surface, at a depth of 0.99 radius fraction plus or minus 0.01. Because we have to measure this in a spherical shell, and we have the slowest polar rotation at this depth, whereas in the equatorial region we have the fastest rotation in 2 or 3 different depths, including this one. So we can now arrive at a number of polar rotations of the Sun over the Schwabe cycle. For the entire cycle, we find 97 plus or minus 2, with the uncertainties around the measurements of the polar angular velocity. And in the rise leg, 37 only plus or minus 1, and in the fall leg, 60 plus or minus 1. So the numbers of polar rotations in the 3 cases are 36 or 37 probably, 60 and 96 or 97. We shall see later why the upper case with 38 rotations or 98 rotations is not retained, and why 61 or 59 are not retained. This is the relevant sensitivity analysis, where we see that if we use 38, the sum for the cycle will be too high and cannot be retained as realistic. Same here for the highest case, and same here for the lowest case. So we are left with a scenario in which we have only 60 rotations of the pole for the fall leg, and only 60 also in this case. That's why we exclude 61 and 59. We now turn to the number of equatorial rotations, and this amounts to 157 plus or minus 1. The uncertainty is only plus or minus 1 because we have a narrower band of estimates in the case of the equatorial rotation compared to the polar rotation. And in the case of the rise leg of the Schwabe cycle, it will be exactly 60, at least less than 61 and more than 51. And for the fall leg, 97 plus or minus 1, likely 96 or 97. So what we find is, all in all, in the numbers of rotations, polar or equatorial, for the fastest and the slowest cases, a set of 4 numbers, 37, 60, 97, and 157, which we find in succession in a recursive sequence, which is a generalized Fibonacci sequence. There is a main Fibonacci sequence, and then there is a set of generalized, so-called generalized Fibonacci sequences, the first of which is the Lucas sequence, and the sequence in which we find the polar and equatorial rotations of the Sun, which we just suggested, is the third such generalized sequence. The order, so-called order of the generalized Fibonacci sequence is defined by an index which we can call K, which is has the value of the number consecutive to 1 in the relevant sequence. In the case of main Fibonacci sequence, 1 is followed by 1. It is also followed by 2 because the Fibonacci sequence is 1, 1, 2. So these are really the 2 first Fibonacci sequences, but they amount to the same one. The first one that is distinct has K equals 3 and is called the Lucas sequence. It was studied by Mr. Lucas in the 19th century, and it is 1, 3, 4, 7, 11, 18, etc. The next sequence is the sequence in which we find our rotation numbers at the pole and at the equator. It has K equals 4 and is 1, 4, 5, 9, 14, 23, 37, 60, 97, 157. So we can now formulate an overall matrix of the solar ball rotation numbers over the Schwabe solar cycle based on the findings that we reached in part 1 of the Fivefold Sun project for the length of the solar cycle and for the angular velocities in the solar ball. In the rise leg, we have 37 rotations at the pole, 55 in the rigid zone, and 60 at the equator. In the fall leg, we have 60, 89, and 97, so that in the overall Schwabe cycle, the 2 legs add up to 97 at the poles, 97 polar rotations for the slowest rotation at the pole, 144 rotations, rigid rotations in the solid body inner part of the Sun and at the latitude where this rigid rotation is also verified at the up to the solar surface. And in the equatorial region, the fastest rotation amounts to 157 rotation for the entire Schwabe cycle. As you can see, in such a matrix, there are mutual ratios between lengths of the legs, which amount to about 1.618. And there are also mutual ratios between the pole and equator number of rotations, which amount to about 1.618. So this is an interesting set of conclusions which we could arrive at from consideration not of the length of the solar cycle expressed in terrestrial units such as terrestrial years. Why would we in fact contemplate an investigation or an understanding of a star in terms of lengths that are those on which a planet, among others, revolves around this star. Is this meaningful?